Now we will solve some examples on linear momentum. So the first example is about the ballistic pendulum. It's an apparatus used to measure the speed of a fast-moving projectile, such as a bullet. So here is a bullet. It has an initial speed v1a, you can see here. A projectile of mass m1 is fired into a large block of wood of mass m2, suspended from some light wires. The projectile embeds in the block, so it's going to be inside the block, and the entire system swings through a height h. How can we determine the speed of the projectile from a measurement of h? Now, first thing I want you to notice is that this bullet getting embedded inside this block is decelerating inside the block to stop with respect to this block. Therefore, we have deceleration and there is a friction that is responsible for this. So this cannot be a process that conserves the mechanical energy of this of the bullet of the system. The process of the collusion between M1 and M2, and therefore since we have no external forces acting on the system of M1 plus M2 and these wires here, we should have momentum conservation, but at the same time not kinetic energy conservation in this collusion process. Therefore, this is a perfectly inelastic collusion. So, first of all, we note that this is a perfectly inelastic collusion. Perfectly inelastic collusions are ones where we have two objects that are colliding, sticking together. And in this case, we have no kinetic energy conservation for the collusion process because we have non-conservative internal forces in action, which is friction. All right. However, when we look at the system of the two blocks and the wires, we see there is no external force acting on it. The total external force acting on this system is 0 in the x direction, you can see, and therefore we must have delta p, so that's called this for x component. Therefore we must have a momentum conservation on the x-axis. Delta px should be 0, so that we have the initial momentum p initial, which is m1 v1 I hat, so m1 v1 a I hat. This is equal to m1 plus m2, which is the final velocity we call vb. So we find that vb should be equal to, in this collusion process, m1 v1a divided by m1 plus m2 in I hat direction. Okay, so this is a result of the fact that for the system of m1 plus m2, we don't have any net external force acting on the x-axis. Well, there's the tension on these wires, but that's on the y-axis. So let me clarify that this is my x-axis, this is my y-axis. All right. After the collusion, we have the tension in the wires acting on the system and the gravitational force. So we only have conservative forces acting on the system. So after the collusion, only conservative forces uh, tension and gravitational force acting on the system of M1 plus M2. Therefore, we can talk about energy conservation. Okay, so having conservative forces acting on the system, the change in the mechanical energy of the system after the collision is 0. So we have delta K plus delta U is equal to 0 after the collision. And delta U, the change in the potential energy of the system, is U final minus U initial. It's going to be equal to M1 plus M2 GH, the final potential energy of the system, gravitational potential energy, and the change in the kinetic energy, delta K, is K final minus K equilibrium. The system will stop at the maximum point, so 0 final kinetic energy. Initial kinetic energy is 1/2 M1 plus M2 VB square. So you can see that the change in the kinetic energy minus M1 plus M2 VB square must be equal to the change in the potential energy minus the change in the potential energy minus M1 plus M2 GH. M1 plus M2 will disappear, so that we will find VB, the speed after the collision, to be equal to square root 2GH. And since we have V1A before the collision equaling M1 plus M2 times VB over M1. So from this equation here, you can see V1A is M1 plus M2 over M1 times VB. M1 plus M2 over M1 times VB. We can basically write this came from momentum conservation on the x-axis during the collision. We can write the initial speed to be m1 plus m2 divided by m1 square root 2gh. Okay. So to summarize, we have a particle, a bullet with mass m1 colliding with a block of wood with mass m2, getting embedded in it, making a perfectly inelastic collision. In the collision process, since we have deceleration of m1 inside m2, we have non-conservative internal forces present. That's friction that is stopping m1 inside m2. So we don't have kinetic energy conservation, but there is no external force on the x-axis. So momentum on the x-axis, linear momentum, must be conserved. So we can write VB in terms of V1A, M1 V1A divided by M1 plus M2 in I hat direction. That will be the velocity right after the collision. Right after the collision, the friction is not present anymore. We only have gravitational force and tension acting on the system. Those are conservative forces, and the system gains a potential energy M1 plus M2 GH in the expense of losing kinetic energy. The system will stop at this point in the maximum height. So we can write a mechanical energy conservation delta K plus delta U equals to 0, which gives us Vb equals square root 2gh, that's the final velocity after the collision. And for the velocity of the first particle, first bullet, v1a, before the collision, we have m1 plus m2 over m1 vb from linear momentum conservation on the x-axis. And this gives us m1 plus m2 over m1 square root 2gh for the initial speed of the projectile. So that's how we can determine the speed of the projectile from a measurement of h. Let's move on to another example. A block of mass m1, 1.6 kilograms, initially moving to the right with a speed of 4 meters per second on a frictionless horizontal track, collides with a light spring attached to a second block of mass m2, 2.1 kilograms, initially moving to the left with a speed of 2.5 meters per second. The spring constant is 600 newtons per meter. So m1 moving to the right, m2 together with this spring moving to the left. Find the velocities of the two blocks after the collision. Determine the velocity of block 2 during the collision at the instant block 1 is moving to the right with a velocity of 3 meters per second. Determine the distance the spring is compressed at that instant. Okay. And once again, I note that there is no friction in this process, no non-conservative internal forces. Therefore, the type of collision I will have here will be an elastic collision. Okay, so I start with identifying the type of the collision. Since there is no friction, we have no non-conservative internal forces acting on this system of two masses. This is an elastic collision. Okay. For the system of m1 plus m2 on the x-axis, so this is my x-axis, I don't have any net external forces acting on the system. Net external forces on the x-axis is 0. Therefore, linear momentum must be conserved on the x-axis. So m1 v1 initial plus m2 v2 initial, the initial momentum of the system of m1 plus m2 must be equal to m1 v1 final plus m2 v2 final after the collision process. Now note that this is a one-dimensional collision, and when I have head-on elastic collisions, if I consider the fact that there is no non-conservative forces, kinetic energy is conserved, delta k is equal to 0. This gives us v1 initial plus v1 final equals v2 initial plus v2 final. You can recall this from our previous lecture. So if I substitute for m1 1.6 kilograms, so 1.6, v1 initial is 4 I hat, m2 is 2.1 in minus 2.5 I hat direction. That's the initial linear momentum. Then I have m1 1.6 v1 final, m2 2.1 v2 final. So this gives us 6.4 minus 5.25 I hat equals 1.6 v1 final plus 2.1 v2 final, and finally we obtain 1.6 v1 final plus 2.1 v2 final equals 1.15 I hat. So let's call this result star. So this is our first equation. The second equation that connects final and initial velocities is the one that utilizes both kinetic energy and momentum conservation for head-on elastic collisions. V1 initial plus V1 final, so 4I hat plus V1 final must be equal to V2 initial minus 2.5 I hat plus V2 final. So we obtain the following result: V2 final minus V1 final is equal to 6.5 I hat. So let's give 2 stars to this equation. Now if I take the 2-star equation and multiply it by 1.6, I will obtain 1.6 V2 final minus 1.6 V1 final equals 6.5 times 1.6, 10.4 I hat. Then I take my star equation, which is 2.1 V2 final plus 1.6 V1 final must be equal to 1.15 I hat. So this is my star equation. And I add these two equations. So let's add them up. And as you can see, we will have 1.6 V1 finals cancelling in this addition process, and we will obtain 3.7 V2 final equals 11.55 I hat. So this is going to be 11.55 I hat, and that will give us for V2 final 3.12 I hat meters per second, and for V1 final I can utilize the 2-star equation, which gives me V1 final equals V2 final minus 6.5 I hat. So I find V1 final to be minus 3.38 I hat meters per second. Okay. Now we can move on to part B of this problem. So this is what will happen when the collision is complete. Now we have V1 initial 4 I hat meters per second, and V1 prime is the intermediate velocity during the collision. It's going to have an instantaneous value 3 I hat meters per second, and V2 initial is minus 2.5 I hat meters per second. Now what will happen during the collision process? You can visualize here the spring will be compressed a little bit. So part of this initial kinetic energy will be stored as potential energy inside the spring, so I have to take that into account. So let me write that at the instant we have the prime velocity V1 prime 3 I hat meters per second. The spring will be partially compressed so we cannot use kinetic energy conservation for elastic collisions, since at that instant part of this energy is stored as potential energy in the spring. Okay, so that's during the collision. But if I consider the system M1 plus M2 for the system M1 plus M2 plus the spring altogether, there is no external force acting on the system on the x-axis, so I should have delta px equals to 0. So if I write m1 v1 initial momentum of m1, m2 v2 initial momentum of m2 must be equal to m1 v1 prime plus m2 v2 prime. I don't have a mass for the spring, it's a light spring, so there is no contribution to the momentum from the spring with this approximation. And you can see that since I cannot use kinetic energy conservation, at this instant I cannot write v1 initial plus v1 prime equals v2 initial plus v2 prime. This is not correct. So let me remind that to myself. Now, if I plug in the numbers, 1.6 kilograms for M1, 1.6, V1 initial was 4 I had, M2 is 2.1, V2 initial is minus 2.5 I had. This is 1.6 M1, V1 prime is 3 I had, and 2.1 V2 prime I want to determine. So 6.4 minus 5.25 I had is 4.8 I had plus 2.1 V2 prime. So I obtain 6.4 minus 5.25 minus 4.8 gives me minus 3.65 I had. This is equal to 2.1 V2 prime, and I find V2 prime to be minus 1.74 I had meters per second. Okay, and part C, I want to know the compression in the spring. Since I have no friction, kinetic friction is 0, the mechanical energy in the system is conserved, so delta K plus delta U must be equal to 0. So in order to determine the compression in the spring, all I have to do is to calculate the initial kinetic energy of the system, which is 1 over 2 m1 v1 initial square plus 1 over 2 m2 v2 initial square. So this is 1 over 2, 1.6 kilograms times 16 plus 1 over 2, 2.1 kilograms times 2.5 square. That gives us 12.8 plus 6.56. The initial kinetic energy is 19.4 joules. The primed kinetic energy during the collision process is 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. This is 1 over 2, 1.6, 3 square, which is 9, plus 1 over 2, 2.1, 1.74 square, and that becomes 7.2 plus 3.18. You can see the primed kinetic energy is 10.4 joules. So there is a loss of kinetic energy, delta K, 10.4 minus 19.4 minus 9 joules, which is equal to minus the change in the potential energy. Therefore, the change in potential energy is 9 joules, which is stored in the spring as 1/2 kx squared due to our conservative restoring force. And this gives us for x square root 18 divided by 600, which is our spring constant, and we find the compression to be 0.173 meters. Okay, now to summarize, in this problem we have an elastic collusion. There is no friction in the system. First, I considered the linear momentum before the collusion and linear momentum after the collusion. They should be the same because I don't have any external forces acting on the system of spring M1 and M2. There is no external force. And the spring is a light spring, so I don't consider its mass. The momentum conservation for head-on elastic collusions with the kinetic energy conservation gives me these two results, and if I substitute the numbers, I can solve for the final velocities, v1 final and v2 final. Now, during the collusion, at a certain instant, we have an intermediate velocity of m1. So you can see that initial velocity was 4 I hat. Final velocity is minus 3.38 I hat. And at some point, between 4 and minus 3.38, m1 had a velocity 3 I hat. And at that point, the spring is compressed a little bit. I have a part of the kinetic energy stored as potential energy. I can still write the momentum conservation between the initial velocities, initial conditions and intermediate conditions. However, I cannot write kinetic energy conservation because I have the spring storing some potential energy, so the second equation for head-on elastic collusions is not valid. So this gives me V2 prime, and if I look at the change in kinetic energy of the system, 1/2 m1 v1 initial square plus 1/2 m2 v2 initial square. Initial kinetic energy 1/2 m1 v1 prime square plus 1/2 m2 v2 prime square. Intermediate kinetic energy, the difference is 9 joules, which is the energy stored in the spring as 1/2 kx square, the conservative restoring force, potential energy, and this gives me a compression of 0.173 meters. Now, before we move on, I want to introduce an important theorem between momentum and impulse. So when you have an external force, net external force acting on the system, mass times acceleration, which is equal to dp dt by Newton's second law, you can see that the net change in the linear momentum of the system is the integral during the collusion time, the net external force times dt integrated from 0 to tc. So this integral, net external force times dt integrated over time, is what I call impulse. It's a vector, and you can see it's going to be measured in Newton seconds. That will be the unit. And the impulse momentum theorem tells me if you don't have linear momentum conservation, you have impulse momentum theorem. The change in the linear momentum is equal to the impulse. Okay, so here is an example. A block of mass m attached to a horizontal spring, spring constant k, is kicked with an impulse I. So we kick it with an impulse I. As you can see, this is initially at rest, and there is no friction in the system. Find the maximum compression in the spring. Okay, now I can use impulse momentum theorem. Impulse, which is the integrated force times time during the time of the kick here, is responsible for the change in linear momentum, which is P final minus P initial, the final momentum will be mv in I hat direction. The initial one is 0. So I find that the the final velocity will be the impulse I divided by mass m. Now I'm going to have no change in the mechanical energy of the system after the kick. So after the kick, I have no friction acting on the system, no non-conservative forces. So the change in kinetic energy plus the change in potential energy will be 0. So during the kick, I apply the impulse momentum theorem. After the kick, I apply energy conservation, mechanical energy conservation. Final kinetic energy is 0. Initial kinetic energy, which is the kinetic energy we gained right after the kick, 1/2 mv square, is equal to minus the change in potential energy minus 1/2 kx square. So this gives us x is equal to v square root m over k. And v was the impulse I divided by m, I over m square root m over k, and therefore we find that the compression in the spring will be impulse I divided by square root m k. Okay, so to summarize, when we don't have linear momentum conservation, we're under the influence of a net external force causing a change in the linear momentum of the system. The net change in the linear momentum is the integral of the net force times dt. So if this is a collusion process, for example, it's a kick like this one, it's going to be the collusion integrated during the collusion time. The impulse momentum theorem is delta P equals I, where the momentum is measured in Newton, impulse is measured in Newton seconds. Okay, so you can see that when I apply force for a certain amount of time by kicking this mass, which is initially at rest, on a horizontal surface where there is no friction, the impulse momentum theorem tells me the impulse is equal to change in linear momentum, so I gain a speed which is I over m. And right after the kick, I gain a kinetic energy, and this kinetic energy will be converted to potential energy as I compress the spring. Since there is no friction in the system, mechanical energy is conserved. So the maximum compression I find to be I divided by square root mk. Maximum compression corresponds to 0 final kinetic energy.